The magic of field trips. Harry Reid is attributed to have said, "The best geologist is he who has seen the most rocks." Well, definitely, the more rocks you see, the better the geologist you will be, because when we're looking at the rocks, we learn to interpret them and understand the clues. The more practice you get at this, the better at it you will become. And this is something you can do wherever you find yourself. And my goal this evening is to encourage you to get involved and participate in organized field outings. So tonight we're going to look at how we identify marine clastics and deep and shallow, continental alluvial fans, different fluvial deposits, identify soft sediment deformation, syntectonic deposition, and we'll also take a brief look at mantle emplacement. And we're going to do all that in 30 minutes. Now, if we take a look at a cross-section of a subduction zone, you have a downward moving plate and an overriding plate. And the sediment and rock that's riding on top of these plates gets squished. Obviously, it bulges up to form mountains. And the tectonics are that there'll be a lot of thrusting and faulting with the splaying out of rocks to the north in this particular case and to the south. And these rocks will be, as I say, folded and faulted. And on top of these plates, we also have smaller basins. And each of these basins will have their own faults and structures which will resemble that of the overriding subduction zone. So, as I said, we're going to take a look at a lot of examples from the Jaca Basin, and that is highlighted here in the southern foothills of the Pyrenees. And to get there from Barcelona, we have to travel across the Ebro Basin, which is here. Now, the Ebro Basin is a fairly flat-lying basin, and it's seen as a 4-deep basin. So we'll touch on that later in the talk. Our first stop was to look at shallow marine deposits. And these were characterized by fossils and ripple marks. So we were able to identify them as being shallow marine based on those two things. Now here we're looking at beds of blocky sands, which are dominantly medium grained, and the less resistant sands are a fine to silty grained. And if we want to have a quick look at the finer, less resistant beds, here they are, fairly laminated and fairly brittle. So our next stop was further northwards in the Jaca Basin, and we would imagine we were going to go into deeper water deposits where we would expect to find a lot more argillaceous material and mudstones. Instead, what we came across was this. As you can see, we have a series of blocky beds, blocky sandstone beds, with finer grained material interbedded. And these are turbidite deposits. Now, turbidites enable the coarser material, the sands which you get on the continental slope, to come down into the deeper basin. And turbidites are characteristic in that they fine upwards. Now, of these turbidites, what we saw, apart from the fining upwards, was that they had sole marks, they had fossils, trace fossils, and they also showed there was a singular mud volcano seen, a very small one indeed. And these are the trace fossils we saw in this one bed. Now, The key here is that they fine upwards, and here you can see them fining upwards. You might say, well, that's downwards, and the fact is that these beds were overturned, and we were able to tell that and determine that from the bottom structures, the trace fossils, and the mud volcano. Now, these beds, being further north in the north end of the Jaca basins, were actually dipping to the south. Now, to remind ourselves of the turbidite model, we have the continental shelf where the sediments accumulate. Then you'll get some form of earth movements which will trigger a mass debris flow, and that will flow downwards, cutting a channel, and these will flow rapidly down the continental slope in a turbulent flow. And the channel shape will be quite narrow at the start and will become wider and wider the further it is away. And turbidite deposits are characterized by what we call a boomer cycle, boomer sequence, and they are seen to be fining upwards. Now, depending on the proximity of the actual unit that you're looking at, if you're looking at the proximal end of the flow, you'll see this very coarse-grained rock fining upwards in this manner. But if you're at the distal end, you'll see maybe a fine sand grading up to a very muddy rock indeed. Okay. Now, if we look through the cross section through a turbidite flow, you'll see this, the mass debris flow and the pebbles and cobbles here, sand on top, and similarly finer rock to the toe. Now, moving down to the Tabanas Basin in southern Spain, we see a very good example of the mass debris flow in a turbidite setting. Okay, so we can see the Tabanas Basin is located right in the south of Spain, and this is a great place to visit. It's also where they filmed Lawrence of Arabia and the Spaghetti Westerns, to name but a few. Now, turbidites are characterized by rapid deposition. And when you have rapid deposition, sometimes you entrap fluid with the sediment. The water is unable to escape, and it becomes pressurized. And the water being buoyant and lighter than the overlying sediment, it tries to escape. And sometimes you get these features, which in this particular case is an injectite. And you can see that the fluid has forced its way up through the overlying sand body and has taken with it a lot of the entrained sediment. And you can use this as a way up structure because there's only one way it can go. Now, we do see mud volcanoes in turbidites, and here we see one at Kilver on the North Somerset coast, and this is a turbidite, Carboniferous turbidite sequence. They're also visible down in Bude in Cornwall. But if you really want to see big mud volcanoes, you really need to go to Azerbaijan. 50% of the world's mud volcanoes exist in this region. However, these are not attributed to turbidites. So let's get back to our turbidites, and back in the Tabanas Basin. The other characteristic you see of turbidites is that they look like they're layered. They look like pancakes. And you can see the sands and the shales, the sands and the shales and so forth. The great thing about these is that the package is usually very continuous and they stretch for miles. And here we are with our poles and we are measuring a particular unit and walked along the canyon and the thickness did not change. Turbidites are fairly widespread, and here is a good example of turbidites in the Lager Basin to the northwest of Rome. Here you can see the sand-shale ratio is higher than previously seen in the Tabanas Basin. And that's suggesting that it's closer to the source than we saw earlier. Turbidites are seen quite a lot in the UK, and here we are in Cornwall, where these Carboniferous turbidites have been severely folded, and in this particular case, pushed over to the side. The same Carboniferous deposits are seen a bit further up the coast in Devon at Hartland Quay, and again over on the west coast of Ireland on the Shannon Estuary in County Clare. We see older turbidites up in the Lake District and in the southern uplands. In this particular example, at Moss End Road Cutting, this was quite a large exposure where we could see horizontal and vertically bedded turbidites thrusting. But here in this example, we can see that the thickness of the sands, got a nice blocky sand here and here, are thinner. And you can see the interbedded mudstones. These variable thicknesses of the sands are because of each pulse of sand, each pulse of sediment will be different. And obviously this pulse of sand that led to this thick unit was obviously a greater amount of sediment in the turbidite than in this particular example. Now, there's always one. I mean, so far you've seen all these turbidites and thought, well, they're fairly easy to recognize. Now we know what we're looking at. But on a recent trip with the Warwickshire group, we went off to Charnwood Forest, and these are Precambrian rocks. And we saw a fairly small exposure, and it all looked like this, all red and weathered. And it was pretty unidentifiable. Now, somebody at some point in time took a hammer to this and created this fresh surface. And on this, we can see that this rock here is a bit coarser grained than that, and it's spinning up to this point where the coarse grained rock starts again. And this is attributed to being a turbidite deposit. Now, obviously, it's not easily recognizable in this particular example. Okay, the transition from marine to continental deposits, I mean, you just don't see it. So let's move straight on to the continental deposits. Okay, this example now, we're in the Jaca Basin at Los Riglos de Malos, and the red rock we're looking at in the foreground, this is a Miocene alluvial fan. And behind it, you have the white rocks are a Paleocene limestone, a nummulitic limestone. And the limestones have been thrust up over the top of the Miocene. And the Miocene itself, this alluvial fan, contains a lot of blocks of the nummulitic limestone. Just going a little bit further up the escarpment, we come across the same deposits, the same Miocene alluvial fan, and we can get a close-up look at these, and we can see that the inclusions contain crystalline basement. They contain cannibalized sandstone boulders of the same age, and we also have this nummulitic limestone. And what they look like is this absolutely atrocious sorting. No sorting whatsoever, effectively. You've got big boulders, you've got cobbles, you've got pebbles, and it's all held together by this red sand matrix. But also at Aguero, we see an excellent example of syntectonic folding. Now, what do I mean by syntectonic folding? Well, in a basin, in an active tectonic belt, the basin is being compressed as the basin is infilling. So the older the sediment in that basin, the more tectonic stress it's endured. And obviously the as the basin is filling in, the older rocks are being compressed and are starting to fold as new sediment gets laid on top. So what we end up with is something like this. In the younger sediment, you can see a little bit of folding taking shape here. Slightly older sediment, you can see the folding is more pronounced. And down here, you can see that fold is very significant. The fold axis is becoming more acute. And right down in the bottom of the valley, that axis becomes very acute. So that is what we mean by syntectonic activity. Okay, getting closer to home, we find alluvial fan deposits up the west side of England. And here we are in the Mendips. And this alluvial fan contains lots and lots of Carboniferous limestone. And this Carboniferous limestone source literally is a couple of 100 yards away. Getting a little closer to home, we have other examples of alluvial fans in the Haffield breccia in Worcestershire, and similarly the Clent breccia a little further north. In the West Midlands, we have the Hopworth breccia in Walsall, and in North Warwickshire, this is what the Hopworth breccia looks like. It's a poorly sorted unit of sand, but you see also that it's a lot finer grained in total than we saw at Allegro. However, go further north still and to Cumberland and Kirby Stevens, and here we see a lookalike example to what we saw in Aguero. Big blobs and cobbles. Now, if we go a bit further west of here and look at the Sedberg conglomerate at Sedberg in Westmoreland, we're seeing a very similar rock type, but what we're starting to see is a little bit of layering creeping in, or bedding. And I'm just wondering, is this potentially what was an alluvial fan starting to enter into the fluvial system to get this sorting taking place? Fluvial conglomerates, as seen in this example, are normally found close to the source of the material and usually form in braided river systems. These are relatively immature rivers, and the amount of conglomerate is obviously dependent upon the flow regimes at the particular time, with high flow regimes depositing the conglomerate, and as the flow regimes wane, we get the settling of the sand. So in this particular example at Gallipienzo in the Jaca Basin, from the top of the hill and to the bottom of the hill, a traverse will yield 6 cycles of deposits. Now, interestingly enough, the younger deposits at the top of the hill were more conglomerate dominated than the older deposits at the bottom of the hill, which were more dominated by the sand deposits. And this is suggesting that the source of the conglomerates was getting more active as it got younger, and this will be related to the tectonics going on in the basin at that time. Right, here is the matrix of the conglomerate. It's a very coarse sand, and you can see it's fairly poorly sorted. The sand units are discontinuous, and they're sometimes at the top, they are very, very fine and form little sheets, very laminated indeed. The conglomerates usually have an erosive base to them. Therefore, we have this overall finding up sequence going on in any particular unit of conglomerate sand. But in this particular example at Gilipienzo, from the bottom of the sequence all the way up through the 6 cycles that were observable, we had an overall coarsening up. Now we can see fluvial conglomerates closer to home. And here we are at Polesworth in North Warwickshire. This is Roundbury Quarry. And here's a picture here. And we've got the conglomerate with the sand on the top. And within the conglomerate, you can get log or coarsening up, which of course is a classic braided stream deposit. But overall, you've got a fining up as the sand deposits down in the lesser, in the waning flow. Closer to home still, we have fluvial conglomerates at the base of the Kenilworth sandstone, seen here at Gibbet Hill Road. At Kenilworth Castle Quarry, there is a breccia, a localized breccia, midway in the Kenilworth sandstone. And as we get further south and in younger rocks here in the Triassic, we're not seeing any conglomerates of any note here. A few pebbles, yes, but not much. And this is taking us into a different type of fluvial deposit entirely. And here we're seeing lots of cross beds, and in particular cases, a couple of channels seen at the same level. And that suggests that these deposits at Guy's Cliff are not meandering rivers, but the model we have is this anastomizing river type. So you have a wide river valley. It's dominated by sand, therefore it's getting a little bit more mature, and there's some meandering going on within the system itself. But overall, it's an anastomizing river. It's got several channels flowing at any one particular time. Back in the Jaca Basin at Patilla de Aragon, we saw evidence of a more mature river deposits. And here we see a couple of upstanding blocks, rocks. And these pillars are actually vertically bedded. So these are beds of rocks, and there are quite a number of them. And I did a traverse between the two of these rocks, these harder rocks, and in between we looked at the softer sediment too. Now, here's the blocky units, the vertical hard rocks, and they're made of medium-grained sandstone. It's fairly clean, it's well sorted, and it is not being ductile, and it has fractured severely during deformation to give you what looks like a wall structure. In between, the rocks are made up of silts and very fine sand. And there's a bit of argillaceous material in there, enabling the rocks to deform without brittly fracturing. These beds, there was lots of rootlet beds here, and indicative of soil development. And this is telling you that these deposits dried out frequently. And this is all pointing towards a meandering river system. We also saw some evidence of soft sediment deformation taking place. In other words, there was a lot of fluid captured within the sediment. We see soft sediment deformation closer to home here at Rowington in the Arden sandstone, and here we can see an overfold in the main channel. And here we have the cross-bedding and a channel in this exposure. Another meandering river deposit is seen here in the Kenilworth sandstone at Kenilworth Cutting. Okay, in Another exposure in the Jaca Basin, we went to Puerto Rio Gallego, and this is a road cutting, and the exposure was massive. It went for quite a long way. I did a 20-minute walk along it, so that gives you an idea of the distance. And this was initially proposed to have been a meandering river system, but in such an exposure that you see a lot of different structures, we couldn't find any evidence of point bar development, which you would expect in a meandering river system. There was no evidence of any rootlet beds, rootlets, or no carbon, no soil development. So all these things that you'd expect in a meandering river system, we could not find. So what we did see was this little thing here. This is what looks to be like a channel with another channel cutting through it. So if we carry on round to the right, and that channel comes up and it comes up that way. So we're looking at 90 degrees to the flow direction of the river at that particular time. But similarly, we saw another channel up here, and then we saw another couple of channels within this section. And this is telling you you've got multi-story channels or stack channels. And this is telling you that the actual river channel is not migrating around, but it is fairly fixed. It's not moving at all very far. And off to our left, we had these beds. We had these blocky beds and finer beds. So, and somebody said, well, is this laminar flow rather than cross bedding? But no, it isn't laminar flow because it's fining up. So you've got these medium sands. Well, it's fine to medium sands actually going into very fine to very fine sands, and then another influx of medium sand and so forth. And the fact that there's no evidence of drying out at all, there's no indication of soil development. These look like to be, you've either got your a wide river valley that's continuously or almost continuously covered in water, which I guess would make it a lake. So, but the sediment supply has been massive. I mean, you've had this subsiding basin and huge amounts of sand coming into the system to give you these thicknesses of units. Now, closer to home, if we take a look at Shirley Canal cutting, we can see laterally extensive beds. Yeah, they're not the same thickness because the sediment supply is nowhere near as high, but we're not seeing any evidence of cross-bedding or channels. So, and it is believed that these beds could be part of a lake at the time of deposition. Okay, I think that's enough on the fluvial systems, enough examples. Let's do something completely different. We're going to go across to Salinas de Oro, which is a lot further to the west, well outside the Jaca Basin, and we're going to look at some mantle emplacement. Now, it's associated with salt, which is quite unusual. Now, the topographic feature, you can see this depression here, and you can see this escarpment here, and you see that escarpment on this geological map is a fault, and this depression here is pink, which is salt, and the blue is peridotite. Now, peridotite and salt are not common bed companions, that's for sure. Now, here's the fault scarp, and well, that's very clear. I mean, a blind man could see that, I think. And this is the salt diaper. You go down into it. And this is at the bottom. These rocks here, and there's plenty of it. And this is peridotite. Now, how do you get peridotite in next to and within a salt diaper? And the answer that has been postulated is that the salts during the Triassic we were all in it was all in Pangaea, and of course you had the Triassic with the influxes of marine sediments which evaporated to give us the salts. And then you've had the opening of the Atlantic and the Bay of Biscay with rifting taking place. And each time the rift occurs, it brings the mantle up a bit closer to the surface. And each subsequent rift has brought it closer to the surface till it became juxtaposed against the salt deposits, as we see in this schematic. And that's the idea. Whether or not it's true, I don't know, but it's as good as we're going to get. A more common method of getting mantle to the surface would be in the form of volcanic vents. In this example, from the German Rift Valley, in the southern German Rift Valley near Freiburg, we have all these yellow blobs, which are olivines. That's what they look like up close. And they're yellow and not green because they've been eroded or weathered. Sorry. The same mechanism is taking place at Lanzarote, where you have the olivines in the volcanic rock. Getting closer to home, we have mantle material in the form of serpentinite at the Lizard in Cornwall. So you think, oh well, okay, I should be able to see this one in a few locations around the place. So take a trip to Anglesey and you see something very similar and you think, oh, okay, is that serpentinite? And the answer is no, it isn't. This green rock, believe it or not, is basalt, and this red rock is jasper. And the jasper has formed from the radiolarian ooze that was lying on the ocean floor. Wow. Well, if you'd have recognized that in the field, you'd have been a top geologist. That is a challenge. So then, in summary then, we've looked at some very young rocks in the Pyrenees, and with these long and good exposures, it's fairly easy to understand what's going on. You can quickly picture and get the model quite clear. And I think it's fair to say the more practice you get, the better at it you become, because then you're able to start to see some lesser exposures as we see in the UK and start to identify them accordingly. However, it really does help when you're working with other people. You know, you exchange ideas and you work your way through saying, well, it's not this, it's not that, so it must be that. However, no matter how much you do this, you will always find one challenge and something that really surprises you. Thank you very much.